Authored by veteran chemistry teacher Abdul Shakur, these two textbooks provide all the essentials that would not only enable students to master grade 11 chemistry, but to excel at the next higher level in this subject. What make these texts unique are their creativity and profundity with which concepts are explained for clarity and mastery. The following is one of a set of 44 different tutorials created by the author, using materials primarily from the text Chemistry 11 in Focus. I hope you enjoyed this video. If you liked it, please give it a thumbs up and don't forget to subscribe. We will see you in the next video and thank you for watching.
Today we'll be talking about wastewater treatment, or what is sometimes called sewage treatment. These two terms are used interchangeably, so it doesn't make a big difference. We'll be talking about the importance of water, wastewater or sewage treatment, water purification, and Canadian guidelines for drinking water. The importance of clean water. Of all the available water on the Earth's surface, less than 1% is fresh and suitable for drinking. Approximately 97.5% is saline and unsuitable for use, while the rest is stored in the polar ice caps. Since drinking water is one of our most important resources, it is important that it be used conservatively, recycled where possible, and that its natural sources remain unpolluted. Sewage and industrial waste pose the most serious threats to our drinking water supply. Raw sewage contains a host of substances which, if discarded into the environment, could cause catastrophic health and environmental problems. These substances include organic solids, grease and oils, pathogenic microorganisms, nitrogenous waste, heavy metals such as copper, mercury, lead, and chromium, among others. These can enter the body by ingestion of contaminated water or food. It is essential, therefore, that the sewage be treated to remove those substances that are harmful to human health if ingested, or which could cause adverse environmental effects. There are some notable cases of people dying or becoming sick by drinking water contaminated with different substances, or where the environment has been seriously compromised. In May of 2000, 7 people died and hundreds more became very sick in Walkerton, Ontario, by drinking water that became contaminated by a deadly strain of the E. coli bacteria. It was discovered that E. coli seeped from a farm runoff into a well, the source of water for the residents of Walkerton. The bacteria remained undetected only after it wreaked havoc on the residents of Walkerton. In 2016, in Flint, Michigan, over 100,000 residents there experienced elevated levels of lead in their drinking water. It was known that this problem started in 2014, when the water to the city was switched from one source to another in an effort to save the city millions of dollars. It was later discovered that some substances in the new source of water caused corrosion of the old lead pipes, resulting in lead being leached from them into drinking water. For this reason, municipalities treat their water with anti-corrosion agent during its purification process. The new water source was probably responsible for 10 deaths and 77 other people who suffer from Legionnaires' disease. This disease is caused by drinking water contaminated with the Legionella bacteria. In August 1995, in my native country, Guyana, the walls of a huge man-made reservoir containing millions of liters of sludge laced with the waste cyanide from the Omile gold mine broke and polluted over 80 miles of river water. Cyanide is used in extracting gold from its ore and is stored afterwards in these reservoirs for natural decomposition. This accident caused immeasurable destruction to fish and other wildlife. The lives of over 40,000 indigenous people depending on the river for drinking water and wildlife were severely affected. This represented one of the worst man-made disasters in recent history in South America. As the human population keeps increasing, so does the need for drinking water. It does become incumbent upon all of us to develop a more caring attitude in terms of how much water we use to avoid wasting it, and to minimize its contamination from industries and other sources. Nations may eventually have to invest in costly technologies to recycle wastewater or to use solar energy to distill water from saline sources. Wastewater or sewage treatment. Wastewater is used to describe that which collects in a series of underground pipes called sewers. The water that collects there comes from rain, melted snow, sinks, your bathtubs, and what is flushed down your toilets. The sewage component of wastewater consists of a range of substances that include organic compounds, inorganic compounds, and a host of pathogenic microbes. The aim of municipalities is to treat sewage and the ensuing water to destroy the pathogens and to reduce the levels of other dissolved substances to save limits for ultimate disposal into the environment or direct use. We're saying that wastewater enters a network of underground pipes called sewers, which finally collects into a large pipe from which it is pumped to the treatment plant. This figure here represents a schematic view of a typical sewage treatment plant. But what you note is that it is not the way you see it here. Each component here is lying on the ground, but they're drawn like this to facilitate our understanding of how the various operations take place. Okay, it's drawn in this way just for us to understand how treatment happens at different locations on this plant. Nothing is above the other here, okay? All right. So first of all, there's what is called preliminary treatment, and that happens at locations C and B. So from the pumping station, water is made to run through these bar screens here. And the bar screen is so made that it removes debris such as plastics, paper, and cloth that gets entangled with the wastewater. So those things are removed mechanically from here. And then after that, the water is pumped into this container C here, what is called grease and grit remover. The water inside here is slowed down significantly to allow any sandy particles or any small stones that get caught up in running water. So all of these here will settle under the effect of gravity as what is called grit. And the grit here is mechanically removed. Also, what is happening here, compounds such as oily and greasy particles that do not dissolve in water will float at the top of the water here as grease balls, and these are removed mechanically. So up to this point in time here, things are removed mechanically. Then after that, the water goes into the primary clarifier, and there you have certain mechanism within the clarifier that allows the water to slow down to zero flow. That allows a second type of particles to sediment under the influence of gravity, and it collects as what is called a sludge. Any other grease particles that escape separation here are skimmed off from the top here. But most of the particles that get settled here are different from grit. They probably consist of those solid organic materials from fecal material, and they settle out as what is called primary sludge. The primary sludge now is then sent to this plant here, G, that is called the sludge treatment plant. We'll come back later on and talk about this sludge treatment plant. All right? So we're seeing now that the composition of the wastewater is gradually changed. As it comes here, sandy and little particles such as stones are removed. Oil and greasy particles are removed, so it gets clear as it moves here. As it comes here now, the solid organic matter settle out, and some more of those greasy particles will come here. From here, the water is subjected to what is called secondary treatment, and this takes place in E and F. E is called the biological treatment plant, and it can consist of one huge circular basin or a number of these depending on the size and needs of the plant. Each of these basins consists of two zones. One, an oxic zone, and two, an anoxic zone. The oxic zone is saturated with oxygen and maintained at a suitable temperature to make it conducive for the activities and growth of aerobic bacteria. This is achieved by pumping warm air under high pressure into that part of the basin. This oxic zone is deliberately inoculated with a series of aerobic bacteria and some protozoans, and these are utilized to break down organic materials found in fecal matter. The fact that these bugs are aerobic in nature, that is, they utilize dissolved oxygen in water for respiration, underscores the importance for oxygen to be constantly pumped into the water to replenish any depleted oxygen and to maintain aerobic conditions there at all times. To get a better understanding of what happens during biological treatment of the water, we'll have an expanded view of one of these circular basins. So this is the oxic zone. Warm air under high pressure is used to supply oxygen and to make conditions conducive for the bugs to thrive. So inside there, bugs are doing a number of things, collectively called the protozoans and the bacteria bugs. They're digesting the organic matter inside there. Lots of digestion are taking place. The bacteria eating these things, protozoans eating them, and they grow and they multiply. They're also changing some compounds into other compounds. They're also absorbing some nutrients inside here. So gradually inside what is happening here is that the organic components of the wastewater or sewage is being degraded gradually and gradually. The water there stays for 3 hours. It stays there for 3 hours to enable the bugs to do the digestion process there. Another important thing that happens there, if you can remember, one of the main excretory products is urea. Remember, you call urea is what is in urine. So another set of bacteria there, while some of them are digesting things here, another set of bacteria is carrying out a set of activities that I want to show you here. See, inside the oxic zone, some bacteria called nitrifying bacteria use dissolved oxygen to change urea first into ammonia, aqueous ammonia, and these bacteria called nitrifying bacteria continue to do that. They change ammonia form there into ammonium ions. And again, more nitrifying bacteria, another set, we continue to oxidize this into nitrite ions. And finally, the nitrite ions are oxidized into nitrate ions. So inside the oxic zone, a number of things are happening there. Digestion is taking place. The bugs are eating. They're producing other kind of substances. They're absorbing some ions, and they're breaking down the organic material. So look what happens now. At the end of all of that, we're having some nitrate ions that are produced. At the end of 3 hours, the water in the anoxic zone is sent to the secondary clarifier. As this happens, it clears the way for the water from the oxic zone to move across to this anoxic zone, where it will spend an additional 3 hours. To replace the water from the oxic zone, a fresh amount from the primary clarifier is sent there. We'll now look at what happens in the anoxic zone. The anoxic zone is deliberately deprived of oxygen to encourage the proliferation of anaerobic bacteria. No air is thus pumped into this half of the basin. The oxic zone is saturated with oxygen, while the anoxic zone is devoid of oxygen. Note, there is no physical barrier existing between the oxic and the anoxic zone. Just an oxygen gradient exists between the two. Anaerobic bacteria do not use dissolved oxygen for cellular respiration. Instead, they use the oxygen that is bonded in the nitrate ions. As illustrated here, the anaerobic bacteria break the NO bonds to release the oxygen that they use for cellular respiration. In so doing, the nitrate ions are decomposed to release molecular nitrogen. Carbon dioxide is also produced from subsequent cellular respiration. Nitrate ions can be harmful to the environment as well as human beings. If released into the environment, it can cause algal blooms with their concomitant ecological problems. If ingested in drinking water by babies, it causes what is called a blue baby syndrome. So one of the main objectives of the anoxic zone is for the decomposition of the nitrate ions. The figure here shows how the nitrate-laden water moves from the oxic zone to the anoxic zone, where the decomposition process takes place for the next 3 hours. We shall now return to the main treatment plant. After this period of time, the water is sent to the secondary clarifier F. The composition of the water that goes there consists of a host of living bugs with their different types of nutrients in their bodies, mineral ions, and lots of colloidal materials. The main objective of the secondary clarifier is to cause the sedimentation of much of these as possible out of the water. Some of this is achieved by the insertion of anticoagulants in the form of salts of iron and aluminum. These operate by neutralizing the negative charges on the colloidal material, making them clump together and settle under the influence of gravity. This settled material is called the activated sludge, since it contains organic matter and a host of living bugs. From the secondary clarifier, most of the activated sludge is sent to the sludge treatment plant G. Because of the presence of organic matter and living microbes, anaerobic activities take place here, where the sludge is further decomposed and gas such as methane is released and collected. Periodically, the sludge is squeezed to extract a supernatant, which is then returned to the primary clarifier for further treatment. The solid that remains is full of nutrients and is used to make fertilizer materials. Note that every 3 hours a fresh amount of water leaves the primary clarifier and enters the oxic zone. This new quantity of water must be inoculated with bugs to carry out digestion. This is achieved by the return of some of the activated sludge that is laden with these. Remember that some of this sludge was sent to treatment plant G, so the rest is used here. Note how dynamic the entire process is. In the primary clarifier, 2 things happen. 1. The sludge gathered there is sent to the treatment plant G. And 2. Every 3 hours, wastewater is sent from there to the oxic zone of the biological treatment plant. To make way for this water that is sent there, the water in the anoxic zone is sent to the secondary clarifier. To inoculate the water that was just sent to the oxic zone, there is return of the activated sludge, while the rest of the sludge is taken to the treatment plant G. The supernatant from G is periodically returned to the primary clarifier for further treatment. The total time that the water spends in the biological treatment plant is thus 6 hours, 3 hours in the oxic zone and the further 3 hours in the anoxic zone. So the water in the primary clarifier is now free from most of the solid organic matter. but it is still laden with different types of microbes, some of which can be fatal. Note so far, there is nowhere in the treatment plant where toxic materials such as heavy metals and other poisonous materials are removed. The only treatment that the water receives after that is disinfection to destroy the pathogenic organisms before the water is released for storage until further treatment. To achieve this, the water from the secondary clarifier is sent to the plant H, where it can now be treated with different agents such as chlorine, UV, to destroy the pathogens. We shall now have a very brief review of the entire process. Wastewater that collects at the pumping station is first passed through bar screens to remove large debris. From there, the water is sent to the grit and grease remover. Here, the flow of the water is slowed down to zero to allow solid materials such as sand and small pebbles to settle out as grit. Insoluble materials such as oils and other greasy particles float at the top. These are removed mechanically. From here, the water is sent to the primary clarifier. A similar thing happens here, except that the sludge that sediments the primary sludge is sent to the sludge treatment plant G for treatment. From the primary clarifier, the water is then sent to the oxide zone of the biological treatment plant. The water there is saturated with oxygen and inoculated with microbes. In here, the following happens. Large organic solids are broken down and digested by the aerobic microbes. The main excretory product, urea, is changed to nitrate ions by a series of bacteria. The water spends 3 hours here. After this time, the water from the anoxic zone is sent to the secondary clarifier. The water from the oxic zone moves into the anoxic zone, where nitrate ions are changed to nitrogen gas by bacteria present there. In the secondary clarifier, coagulants are added to cause the colloidal materials and microbes to settle out as what is called the activated sludge. Some of this sludge is periodically returned to the oxic zone to inoculate any new amount of water that arises there from the primary clarifier. The rest of the sludge is sent to the treatment plant G. In G, anaerobic respiration takes place. Some materials are digested with the liberation of methane gas. Periodically, this sludge is squeezed and the supernatant is returned to the primary clarifier for further treatment. The solid that is formed can be used to make different stuff such as fertilizer material. From the secondary clarifier, the water is disinfected in H, where it is treated and released in the storage facilities for further use. I hope that was useful. As you can see, the entire process is very dynamic, so we have to take a holistic view of what is happening around the plant. So thank you so much.